Hey, what's going on, guys? Let's look at this problem right here. Here this question is asking, find an equation that relates the system input and output and also determine the system properties. And if you look at the circuit, here we have a simple circuit and this is in series with a capacitor, and there's a current flowing through the capacitor, and the voltage output is going to be what? When we have a capacitor and if the current flowing through the capacitor, if you remember the circuit analysis class, the Vc of t equation will be given by 1 over c integral negative infinity to t and then I of tau d tau. So when we do the integration, this tau will be replaced with t. Okay, so this is the equation when we have the capacitor and the current flowing through the capacitor. Okay, now let's look at the system properties. There are different system properties we can talk about. Let's talk about the memoryless. Like for a system to be not memoryless, what has to happen is the output at time t depends on input at time t and all past input. And if you look at the integration, this is depends on input time t and also all the past input because it's going from negative infinity to t. So this means this is a not memoryless system, not memoryless. And also we can talk about the causal. Causal is same as not memoryless. Output at time t depends on input at time t and all past inputs. If you look at this one, it depends on like output of time t is depends on input at time t and all the past inputs. So this is also a causal system. And the next thing is we can talk about linear. If a system for a system to be linear, the superposition must hold. For example, if we to check linear, what we can do is if we put the input current as linear combination as to, like, let's say alpha 1 I1 of t plus alpha 2 I2 of t, then if the input is like that, then we have to get an output that should be coming like the, instead of I1 when we integrate using I1, we should get y1 of t, and let's say this is y of t, right? Y of t is equal to Vc of t. So we have to get I1. If we put input I1 of t, we have to get output y1 of t, and when we put input of I2 of t, we should get an output y2 of t. Now let's see whether it satisfies that. Now to check this one, what I'm going to do is I'm going to do the integration. So y of t, we know that from this equation y of t is equal to 1 over c I of tau d tau, but instead of I of tau, I'm going to replace this one with the linear combination. So this is going to be 1 over c negative infinity to t. Then we are going to have alpha 1 I1 of t, alpha 1 I1 of t, and let's put tau because when we do the integration, t will be replaced with tau. Tau will be replaced with t. So let's put tau, alpha 2 I2 of tau, and we are going to integrate with respect to tau. Okay, and then we can separate this one as two different things. Like we can take the alpha 1 to the front since it's a constant. 1 over c integral negative infinity to t I1 of tau d tau plus alpha 2 1 over c integral negative infinity to t I2 of tau d tau. Okay, and if you compare with this one, right here, 1 over c I of tau dc is equal to y of t. 1 over c I1 of tau d tau, actually this is tau, right? D tau. So this tau is going to be equal to what? y1 of t. And this one is going to be what? y2 of t. So finally we are getting y of t is equal to alpha 1 of t, alpha 1 of y1 of t plus alpha 2 of y2 of t. That's what we expect. When we put the input like this, we have to get the output related to, like when we put the input in terms of I1 of t, I2 of t, we have to get an output y1 in terms of y1 of t and y2 of t. That's what we are getting right now. So this system is linear. So we can say system is linear. The next property we can check is we can see whether this system is time invariant. Time invariant is basically delaying the input yield and output, delaying the same amount. Okay, now let's see whether it happens. So let's get rid of this part. Okay, now we are going to check whether this system is time invariant. So what I'm going to do is, first I'm going to delay the time. So let's say y of t. So we have this equation right here. So let's I'm checking time invariant. Time invariant. To check the time invariant, I'm delaying the input by t naught, t minus t naught, and let's call some y1 of t. So y1 of t should get, we have to check, does y1 of t is equal to y of t minus t naught, because when we delay the input by t naught, we have to get an output that delayed by t naught. So if we get that one, it means this is time invariant. Now let's go ahead and see that. So to do that, first I'm going to do the integration y1 of t 1 over c integral negative infinity to t, then I tau minus t naught. When we do the integration, tau will be replaced with t, so tau minus t naught, and with respect to d tau, we are integrating with respect to d tau. So finally, if we actually here it's not very clear. So to see this one clearly, what we can do is we can do one thing, like we can do the substitution. So let's say let lambda is equal to tau minus t naught, and let's d lambda, then d lambda is going to be what? Is d tau. So if we replace that one, this one with that, so let's continue here. So this is going to be equal to what? We are going to have 1 over c remains the same, then negative infinity, instead of t we are going to put tau minus t naught, but in this case we can put t minus t naught. Okay, then I of, instead of tau minus t naught, we are going to replace with that one with lambda, and instead of d tau we are going to replace that one with d lambda. So from this one you can see this is exactly looking like this, right? That's what we want. 1 over c, this integral exactly same but delayed by t minus t naught. So this is what we want. This is our r of t, and not r of t actually. So from this one we can directly say this is time invariant. System is time invariant. Now the last property we can check is whether this is a BBO stable. BBO is bounded input and bounded output, whether it is stable. Now to check this one, let's get rid of this part. Okay, so let's see. So we are going to check BBO stable. We are going to see whether this is stable, like bounded input, bounded output, like stable bounded input. So first let's go ahead and look at a bounded input. I of t is equal to u of t, a bounded input, and let's do the integration. So if it's bounded by a certain limit, it means this is a BBO stable. But if it's not bounded, if the output is not bounded, then this is not BBO stable. Now let's see. Now if we apply the integral, y of t is equal to 1 over c integral negative infinity to t u tau d tau. Now 1 over c. Okay, let's look from 0 to t u of tau dz. So if you look at this one, this is a ramping function. So finally, if you do the integration, this is going to be 1 over c times r of t, because this is r of t, ramping function. So the function is going to grow like this. So what's going to happen is, as the time increases, this is reaching infinity. So this is not bounded. This one grows without bound as t approaches infinity. Okay, so this is not Bebo stable, because there's no limit for this one. It's breaking the limit. So this is not Bebo stable. We can say that's our last property, not Bebo stable. And those are the properties of this system. And that's it. I hope this helps. Thanks for watching.